Or good afternoon, everybody from Oak Ridge. So we're moving into our next discussion, and I will like to introduce our next speaker, Matt Norman, who is in the scientific computing group here with the Oak Ridge Leadership Computing Facility, and he will be leading our discussion of OpenACC directives. So Matt, it's all yours.
Thank you. Let me get the clicker. Does it work? Yep. So my name is Matt Norman. I'm going to be talking to you about OpenACC, really just an introductory talk touching on different aspects of how to use it. I'm a part of the scientific computing group at Oak Ridge, and I've been working with climate models and GPU porting for somewhere around 10 or 11 years. I am going to focus more on GPUs, and there will be somewhat of a focus on Fortran as well. I try to give plenty of examples in C, but some of them will be only in Fortran. There's a reason for that. I would say if you're in C or C++, there are better options than OpenACC in terms of portability. And I know that's a political statement, but I also think it's a true one. But you can use it in C effectively if you want to do that. So what is OpenACC? You've heard a little bit about it before, but it's a set of directives that you apply to loops and that you apply for moving data. And it's also a library API that you can use in the runtime library for simpler GPU programming. It's meant to simplify GPU programming compared to things like CUDA or OpenCL. So the directives that you put in Fortran, they look like comments, and you can see the Fortran syntax says bang $ACC. That's ignored if you don't turn on the OpenACC flag in your compiler. And the same is true for C++. This pound pragma ACC is ignored. I didn't have the microphone on. There we go. Is that forward just a little bit? Step forward even. Is it still quiet? Okay.
Yeah, you're good.
All right. So hopefully you can hear me a little better now. But the gist is you can add these. It'll run on the CPU if you don't turn on the OpenACC flags in your compiler, and it will run on an accelerator target if you do turn on the OpenACC flags. So there's a few main purposes for OpenACC directives. One of them is to apply directives to loops so that you can thread things within the GPU. Another is to manage data between two separate memory address spaces. And another is to manage asynchronicity between the CPU and the accelerator. OpenACC is intended for cross-platform portability. Realistically, it's mostly geared towards the GPU. If you use some compilers, there's an offload for multi-core. But generally, a lot of OpenACC, in terms of at least implementation, is geared toward the GPU. So why would you use OpenACC? It's simpler to use than CUDA. The source code requires fewer changes. It's more portable to other architectures. If you wanted to do a transition to OpenMP offload, it's quite similar to OpenMP, so it'll be familiar to those who are already familiar with OpenMP. And it shields programmers somewhat from the complexity of the hardware, which is a good and a bad. And it provides some conveniences that CUDA doesn't. So let's start off with the first part. Again, there are three uses you see here. The first is to apply them to loops to get things to run on the GPU. So this is what a GPU looks like. It's a collection of vector machines. And so these things are called streaming multiprocessors, and within a streaming multiprocessor, things are pretty similar to what an old vector machine would look like. There's a lot of thread switching and latency hiding. The one thing to keep in mind is each of these streaming multiprocessors, you can coordinate within one, but you can't really coordinate between them, and that's how you scale to a large number of SMs on the GPU. If you look inside one of these, what you'll see is a bunch of single precision cores, half precision cores, and special floating point units and cache. So this is what you're mapping your loops to. Generally, you don't really have to think about this. but sometimes you do. We'll get into that more later. So there's two kinds of loop decorations in OpenACC. There's the kernels directive. This is when you want the compiler to do the parallelization for you. In the ACC kernels directive, everything you say is descriptive of the parallelism. It is not prescriptive. You're letting the compiler do what it wants. Everything you tell the compiler in an ACC kernels is a suggestion. The compiler can ignore it or change it at will. And this is the syntax you see in C and Fortran. I don't recommend using kernels, honestly. A lot of OpenACC folks will tell you to use kernels, but when I use it in practice with Cray and with PGI, it significantly underperforms, even for simple things like setting an array to 0. I really don't recommend using it, at least as it's currently implemented in most compilers. Your best bet is to use the parallel loop form, which is this. So this is prescriptive. This says you will do what I say and you will not change things. This is a lot more similar to what OpenMP already does. Usually when we use the ACC parallel directive, it's coupled with a loop directive altogether as parallel loop, and you apply it to the next loop in your code. Every parallel directive is generally a single kernel on the GPU. So there are 3 levels of threading on the GPU. There's 3 levels of threading in OpenACC, and I'm going to shamelessly map this to the GPU because both Cray and PGI do this mapping, and I imagine GNU is probably doing the same with the Mentor graphics port. But if you say gang, if you remember that slide with the GPU, I should have replicated it. Gang will distribute it across these different streaming multiprocessors. The worker and vector will distribute the threads within one of the multiprocessors. So any loop decorated with worker or vector, that is the true SIMD work on the GPU. The gang is less SIMD, it's more distributed across multiple vector machines. If you know CUDA, these are the equivalents. The grid, actually that should be gang, not grid, but the gang is effectively the grid. It's block ID x.x. And the worker and vector are the XY of the thread ID within a single block. So if you have multiple levels, if you have multiple levels of parallelism, you have up to 3 that you can expose in OpenACC if you want to. If you only have 2 levels of parallelism, I strongly recommend you only use gang and vector, which is the outermost and innermost level of parallelism. But honestly, if you're porting this stuff, I do recommend that you not use gang, worker, or vector. I recommend that you collapse if at all possible, and there's a reason for this. First, if you collapse multiple loops together, and I'll have an example in a second of what that looks like, you're basically gluing multiple loops together into a single level of parallelism. Loop collapsing is often more efficient than explicitly specifying gang, worker, or vector, and the reason for that is oftentimes your inner loops are not sized perfectly for the vector size on the accelerator that you're targeting. And oftentimes, if you do size it exactly what it should be for the vector length, you're tying one of your dimension sizes down and you can't actually change it in runtime. And a lot of applications need to change the loop sizes. So you don't want to tie yourself down to a certain kind of parallelism at every level of your code. So if you can, I recommend collapsing loops down. We'll just jump right into an example. I have a C version right after this if you have a strong aversion to Fortran. So this is the diffusion equation if you were to solve that, which is just a second order spatial derivative specifying the first order time derivative. This is what it would look like, and here we have the I and J loops are collapsed down, where this collapse 2 means take the next 2 tightly nested loops and collapse them down into a single level of parallelism, and just let the compiler and the GPU decide how to distribute that best. This is what it would look like in C, where you loop over a number of steps, and you collapse a couple of loops down to calculate the tendency and to apply the tendency to the state. I'm moving through these slides fairly quickly because I believe most of us learn more by hands-on exercises and not so much by hearing somebody drone on for an hour. So I will try to keep this short. These slides are available if you want to take a look at this code as an example of how to do OpenACC. One thing that I definitely want to talk about up front is the idea of race conditions. OpenACC's simplicity can be really deceptive. Most people are not used to exposing a massive amount of threads. If you're used to OpenMP threading, you're used to exposing maybe tens of threads at most, and now we're asking you to expose on the order of millions. So oftentimes when you do that, you have to expand the threading down into the innermost loops of your code. And when you do that, oftentimes there are what are called race conditions in the innermost loops. A race condition, which has probably already been covered, it's when multiple threads running in parallel access the same memory location in a manner that can cause wrong answers. The most common example of this, at least in most science codes that I have seen, is when you have reductions over an array. And so you can imagine two simultaneous threads will access the array at the same location, and they're just trying to calculate the sum across the entire array. And they both might read the same value, then update it with their own value, and then write a stale value, which what should actually happen is they should update them in order. So this is an example of a race condition that you can encounter. We'll go over a few more examples throughout this. One way you can handle, and probably the most common way, well, there are two common ways, and both of them are going to be shown here. To handle a race condition is what's called an atomic operation, which has been covered. I remember hearing that. And what this does is it avoids two threads accessing the same memory location at the same time. And so if you look at this example of this loop here, you have this variable flux that's being updated in a sum from this other variable, this triple W. But flux doesn't have an I dimension, if you look here. And what's happening is, as you're doing simultaneous threads in the I dimension, multiple of those threads can access the same location and flux at the same time, and you can get a stale update. And the way you handle this is by saying ACC atomic before you actually do that operation. What that says is every thread, once it reads the value, no other thread can read or update the value until that thread has updated it. So that way you don't have multiple threads using stale values. Atomic becomes less efficient the more threads you have accessing it at the same time. So in this case, atomic is extremely efficient because most of the parallelism is still fully parallel. It's only one dimension of these arrays that actually needs to be atomic. So in practice, this will run pretty fast. The other, okay, before we go to the reductions, how do you know when you need to use ACC atomic? And so there's a very simple way to do this. If you look at the variable that's being written to, the variable on the left-hand side of the equals, if it has fewer threads than you're actually looping over, you are guaranteed to have a race condition. So it's one of the easiest ways to look. And so you can look at the flux variable on the left-hand side of the equal sign, and you can say, I see two indices there, but I'm looping over three indices. So this is a guaranteed race condition. You need to handle it with either an ACC atomic update or an ACC reduction. So what is a reduction? A reduction is when you are reducing the contents of a large array to a single scalar value. And usually this is either a sum or a min or a max, are the most common reductions that we have. And this is the syntax that you would use in this case for that race condition. This global sum is going to be accessed by every single one of the threads at the same time. If you were to try to handle this with an atomic update, remember the more threads accessing it at the same time, the worse atomic performs. And in this case, you really want to use the reduction clause because under the hood, the compiler is going to use some of these vendor-provided libraries like NVIDIA's Cub library, and AMD has some of those available too. Intel does as well. And they're going to use those optimized libraries under the hood to do the reduction for you. And this will perform very efficiently in practice. So this is answering the question that I just answered. Do I use atomic or reduction? The answer is if it's a partial reduction, where you're writing a large array to a smaller array, oftentimes atomic will do a better job. If you're reducing an entire array down to a single scalar value, you always want to use reduction. But what you can do is you can actually use atomic or reduction and see which one performs the better in your case. Oftentimes, just checking and finding out is the only way to know for sure. The other thing you need to think about when you are putting loop directives in OpenACC are private variables. A private variable is a variable for which every single thread on the GPU needs its own copy. And the way you know you need a private variable is that it's indexed over a dimension that is not included in the parallelism. So the parallelism that we're exposing here in this 4-level collapsed loop is a loop over elements and then 3 dimensions, vertical and 2 horizontal. In this case, this old grads variable you see here has a dimension that is not included in the dimensions that we are threading over, and therefore every thread needs its own copy of that. Now note, you don't need to use the private clause on scalars. This is different than OpenMP. I believe in OpenMP CPU targets, which is traditional OpenMP 3.x, you have to specify the private clause for scalar variables for which every thread needs a copy. However, in OpenACC, it automatically gives a separate copy of every scalar to every GPU thread. It assumes that you need to do that. So you only need to add the private clause for small arrays, not for scalars. So this is a note on collapsing. So you have to have the loops tightly nested if you want to collapse them. And that can be a problem sometimes because tightly nested means you have, in C, you have 4, 4, 4, and then a bunch of work, and then 3 brackets immediately closing everything off and no work in between. So here's an example of a loop that is not tightly nested at the top in Fortran. And what you're going to have to do in this case is you'll have to move that if statement down to the innermost level inside the do loop to collapse those together if you want to do that. This has no effect on the GPU whatsoever so long as that if statement does not branch for a chunk of, say, 32 threads or so. However, on the CPU, this is probably suicide for vectorization because most compilers either will not vectorize this because of that if statement, or if they do, it would be vectorized poorly. So this is one of those cases where your OpenACC code is not going to be cross-platform, portable, and performant at the same time. Performance portability is a little bit of a unicorn. You can't really do it with exactly the same source, and it's issues like this that usually give the reasons why. So this is just something to keep in mind if you want your code to perform optimally on CPUs and GPUs. This kind of transformation will not perform well on the CPU, but it would be fine on the GPU.
Matt, while we're on can you go back to the previous slide? There was a question, and this seems like a good opportunity to address it. Could you elaborate a little bit more on collapse?
Okay.
I think what they're getting at is what do you mean when you say collapse? What are you telling it to do?
When you collapse, I really should have put a slide in here for this, but take this as an example. You're collapsing 3 loops, the K loop, the J loop, and the I loop. What this effectively does is it creates a new loop that is indexed over nx times ny times nz. So it literally smashes all of these loops together into a single loop that can then be threaded and divided among vector and gang for you under the hood by the compiler. And in my experience, this usually performs better than trying to make, say, the I loop vector, the J loop worker, and the K loop gang. The reason is that oftentimes in these codes, you can't just fix nx to be exactly 128, for instance. And so if you collapse them together, you can allow nx, ny, and z to be whatever you want, and it will perform well. So you're creating a new loop, if you can imagine a do loop over a new variable called ijk that goes from 1 to nx times ny times nz. That's what this is creating for you. Is that a little more clear? Or hopefully, if it's not, just comment in the Slack channel, and we'll try to cover it in more detail later.
Yeah.
The other thing you have to consider when you're writing OpenACC is function calls. Function calls on the GPU must be declared with the ACC routine directive. And this is the syntax in Fortran. If you want the syntax in C, just put pound pragma instead of bang $. And the syntax is you put ACC routine, and in the parentheses you put the name of the function, and then you specify at what level of parallelism it is. So if every single thread is calling that function and there's no GPU parallelism within the function, then you would call it sequential. If that function has, say, vector level parallelism that goes within a streaming multiprocessor, you would put ACC routine name vector. This is an example of a sequential ACC routine where you're looping over the grid in the X, Y, and Z dimensions, and you want to compute some kind of tendency, but there's no parallelism within the tendency calculation. So this is an example of that same heat equation that we saw earlier. We would just declare ACC routine sequential in the actual function, and then when we call it, the compiler knows how to link this properly and have it perform well on the GPU. The C syntax for ACC routine is slightly different because the Fortran compiler has more information about functions because of the module file format. In C, you typically have to put the ACC routine both at the function that is being called and at the call site to make the compiler aware of how to glue these things together. So, are there any more questions on the Slack channel about that?
Specifically about the collapse or
anything that I've talked about previously? I'm about to move to the idea of OpenACC and data.
So there was a statement, looks like gang is by thread or, is thread block or grid, worker is warp, and vector is thread. If that is the case, then mapping is not enforced, very loose. This may lead to thread divergence. Is that a correct statement? If you want to read it, I'll walk my laptop up to you.
If you wanted to specify things like warp, really so vector is the finest level of parallelism. Okay, I'll read it here. Okay, worker is definitely not warp. Let me go back to the slide. This is the slide in question. If you look at the third bullet point here, this is the CUDA equivalent of what you're looking at for gang, worker, and vector. Again, grid should be gang here. I'll make that change. But vector is the finest level of parallelism. So if you wanted to think of a vector as being a warp, you could, but really it's not. It's just the X dimension within a streaming multiprocessor, and worker is the step above that in terms of coarseness. Worker is the Y dimension within a streaming multiprocessor. And gang is the same as kind of a grid in CUDA speak. Gang will spread things across different multiprocessors. So in terms of coarseness of threading, the coarsest is grid and the finest is vector. So I hope that helps answer the question. So if you make your innermost loop vector and your loops are ordered correctly, you won't have any sort of, this may lead to thread divergence. So thread divergence is a concept more related to if statements. So maybe we should cover that separately, but when it comes to thread divergence, if you have an if statement in your code and the innermost loop is diverging one way or the other in the if-else statement, that's going to degrade your performance on the GPU because of this warp idea, but that's actually unrelated to the gang worker vector. That's more related to how the if statement is posed and where it's branching off. But maybe you meant to bring up the idea of coalescing memory accesses, and if you make vector as the innermost and your arrays are ordered so that the fastest varying index is the same as the fastest varying loop, then your GPU memory accesses will be properly coalesced and you'll be accessing the bandwidth effectively. So I hope that answers that question as well. Do we have any others for that part?
No.
Okay. So I'm going to move over to the idea of managing data between two separate memory address spaces. So if I made a cartoon of what it looks like to have a typical GPU and a typical CPU, the CPU has a main system DRAM, which is slower but typically a lot bigger, and then you have this extremely slow bus in between the main memory and the GPU memory. But the GPU memory has a much higher bandwidth, but it's usually a fair amount smaller. For a lot of applications, the reason the GPU outperforms the CPU is almost entirely owed to the fact that you can access DRAM faster. There's a larger bandwidth, a thicker bus going between the compute cores and the memory. So how do we deal with the fact that these are two separate memory systems? So if we go in the traditional OpenACC approach, that's what I'm going to go through first. And then we'll talk about some of the ideas about unified memory address spaces that you get from things like CUDA managed memory, and on a machine like the OLCF Summit supercomputer, you actually have a unified memory address space. So before we start, if you're coding in Fortran, the compilers, at least Cray and PGI, they will generate the data statements for you. And this is incredibly helpful. I recommend you rely on this heavily if you're in Fortran. And if you don't have access to Cray, you can download the PCI compiler for free. They have a community edition that you can get on your desktop that has some simple Quadra GPU or something, and you can use it there. What this allows you to do is to port your kernels first and not even worry about data movement, because the compiler will generate the data statements for you. The data movement will be non-optimal, but it will give a correct result and be running on the GPU. So you can separate your concerns, which is really nice to do. And then you can just deal with the data later. Also, I believe Cray has a flag for this too. I just didn't look it up at the time. But for PGI, you can do this -M info equals Excel, and it will print the data statements that it created as the compiler output. And you can use those as information for writing the data statements yourself. However, in C and C++, you have to worry about the data as you port the kernels because the compiler doesn't know how big the variables are. In Fortran, they use what are called array descriptors, so they know everything about the variable that they need to know, but in C, it's just a pointer. They don't know anything about the extent, so you have to write the data statements yourself in C. In OpenACC, the typical MO is to mirror data between the CPU and the GPU. So typically in an OpenACC workflow, the data will actually exist in both spaces. You declare and allocate it on the CPU first, and then you use directives to allocate it on the GPU. And we'll go over what those directives are, and you can use other directives to move the data back and forth as you do your kernels. So typically you have the same variable, and it has a CPU existence and a GPU existence at the same time. This is something important if you are in the C and C++ realm. All arrays in C OpenACC have to have data bounds. And the reason is the compiler doesn't know how big the array is, so you have to tell it. In Fortran, we have these array descriptors, but C doesn't have that under the hood. But the syntax is kind of awkward for a C programmer. So this is the syntax that you see here. Suppose we wanted to copy data in, which means all of these data statements are from the perspective of the GPU. So if you say copy in, it means bring it to me, I'm the GPU. So it means copy it from CPU to GPU. In this case, you would have to put beginning : size, whereas you might think you should do it beginning index : ending index. That's not how slices, these aren't array slices. It's a different syntax, so especially you Python folks, this is going to be painful for you. But if you wanted to start at, say, index 3 of some array and go to index 10, you would actually do 3 : 8. So just something to keep in mind. You definitely don't want to say 0 : size -1, which is what a lot of C programmers would do by default. You just do size. You don't even need the 0 : if you don't put anything. If you don't have a colon in there, it's assumed that you're starting from index 0. So this is something you really need to keep in mind, you C programmers. This can trip you up. Just want to throw it out there. The slide is here for you to take a look at. These are the semantics of the copy in, copy out, copy and create data statements. I'm not going to go through these here in the presentation. The slides are here as a reference for you. One thing I do want to emphasize, however, is every data statement in OpenACC, you should put a present or prefix to whatever you say. So if you have something that's already been declared on the GPU, meaning there's a pointer mapping between CPU memory and GPU memory already, it's been allocated, it will ignore all of the data statements that happen for that memory location until that is deallocated on the GPU. So if it already exists on the GPU and you say copy in, it's not going to do anything because there's a present or copy in. So if it's present, it doesn't do anything. But if it's not present, then you allocate it and then copy it from CPU to GPU. The reason they do this is so that you can nest these data statements. So if you have data statements on every single kernel in your code, you can put parent data statements outside of that that keeps the data on the GPU the whole time, so it's not constantly being shuffled back and forth. It can be confusing at first, but in the end, this actually is simplifying your life. But you do need to kind of get familiar with the semantics of what these ACC statements mean. So this is an example of potentially shuffling data back and forth, but actually wanting to keep the data on the GPU the whole time between two separate kernels. We have one kernel, again, in this calculation of the heat equation. So we're calculating a tendency and then we're applying a tendency, and at the same time we have this, say, horizontal sum where we want to get, some average column of the state Q. You can ignore that. I actually didn't need that in here, but in this case, you'll see that I have these data statements wrapping around the outside of the code that keeps the data on the GPU the whole time, so that as it keeps calling these kernels over and over again, it's not shuffling the tendency array and the Q array back and forth every single time. So this is an example. The compiler will automatically generate data statements for the two kernels that you see here, the parallel loop. Actually, there's a bug in here. That should be collapse 3 on the bottom one, so I'll have to change that in the slides too. But this is an example of you adding your own data statements outside it to make sure that the data isn't constantly being shuffled back and forth. So if you want to do an intermittent update to the GPU or the CPU, again, if you use copy in, if the data already exists, it's not going to do anything on the GPU. So one way you can get around this is you can use the ACC update, which if you declare an update in the code, update host means take it from the GPU to the CPU, and update device means copy it from the CPU to the GPU. When you use update, it has to already exist in GPU memory space, so you have to have already done a copy in or create or copy. But this will always copy it from one memory space to the other, whether the data even if the data already exists. So earlier, I'm talking about structured data statements. So we have an ACC data and an ACC end data, whereas in C you would have an ACC data with two brackets. There's also unstructured data statements in OpenACC, where you can do an enter data and an exit data. And the semantics of these are slightly different, but I'm not going to get into that in this presentation. I do have resources available that give the semantics of this versus the structured data semantics, but what this allows you to do is to have data statements that don't have a one-to-one correspondence between enter and exit. You don't have to have an exit for every enter. Although if you want the code to run multiple times, that's probably a memory leak, and you'll probably have really bad things happen for the solution that you don't want. So I do recommend trying to have an exit for every enter, where you delete and create variables in a one-to-one correspondence, at least somewhere in the code. But this allows a little extra flexibility for those whose workflow in their model can't operate in a structured environment. So there are other data statements where you can use, say, this present clause, which tells the compiler this data is already present, don't worry about it. This used to be somewhat of an optimization because the compiler's checks and copy in and copy out were very slow for PGI in particular, but they fixed that, so you don't really need to use the present clause. But the present clause, one thing it will do for you is it can be a sort of runtime debugging, because if you say present and it's not present, the PGI and CRAID compilers will typically dump out the entire present table for every variable in your model and say either it's partially present or it's not present and tell you which variable and what line of your code this error happened at. So this can be very useful if you're expecting the variable to be there, but it's not. The compiler will tell you during runtime with an error all of the information you need to find the variable that wasn't actually present when you thought it was. So this can be good for performance tuning in particular. Another thing is you don't actually have to say ACC data. When you do the ACC parallel loop, you can attach data statements to it. Things like copy in, copy out, and copy. And for most people, this is where they first start actually doing data movement, is by adding these themselves. And when you code in C with OpenACC, you have to have copy statements on every kernel. So suppose you don't want to worry about data, you don't want to have to code data statements. I would say managed memory is for you, and I strongly recommend that you try it out. The only compiler I know of that exposes managed memory for you is the PGI compiler. So you would use this compiler flag you see here, this -TA equals NVIDIA comma managed compiler flag. And what this does in Fortran is it replaces allocate calls, and in C it replaces malloc and calloc with CUDA malloc managed under the hood. And what that does is it shifts the burden down to the CUDA runtime for these variables, and if you access it on the CPU, but it was previously accessed on the GPU, it will copy it from GPU to CPU for you. So this will make the variable look like a global address space, essentially. And in my opinion, this makes C OpenACC programming a lot less stressful. These data statements that you add in C are going to look really ugly. I don't think anybody wants to see that in their code. And especially when you're starting out, say with a hands-on exercise for the next few hours, you're definitely going to want to use managed memory, in my opinion. I think it will make things a lot better for you. One of the problems with managed memory is it's very expensive to call a CUDA malloc managed. The PGI compiler has a way around this because it automatically engages what's called a pool allocator, where it allocates a large chunk of managed memory for you, and then it hands out chunks of it under the hood when you call CUDA malloc managed. So this makes the calls for CUDA malloc managed a lot less expensive, and they turn it on automatically if you use managed memory in the PGI compiler. Another problem with managed memory is when you allocate the variable with CUDA malloc managed, it only allocates it on the CPU at first. It doesn't do anything on the GPU until you first touch it in a kernel. And the moment you first touch the variable, then it allocates it. And so what it looks like if you were to profile that kernel is a really long latency for the first access of the variable. The way you can get around that is this routine here called CUDA mem prefetch async. And that will automatically allocate the variable on the GPU immediately, so that when you actually get to the kernel, you're not waiting for the allocation to finish before you can get data from that variable. So are there any questions regarding data statements before I move on to the idea of asynchronicity?
There's one, does OpenACC support unified memory like in CUDA? But there's kind of an answer to it already posted. You kind of mentioned it.
Yeah, that question was probably before I talked about managed memory. OpenACC has no native support that I know of for managed memory. From what I understand, OpenMP5 is supposed to have some kind of universal memory address space as a part of the standard for OpenMP offload, but that's to come. OpenACC does not expose this idea explicitly. I don't know how you would do it yourself in a performant way if you don't use the PGI compiler, especially if you're in Fortran, because Fortran has these array descriptors which would presumably need to be in managed memory as well, and not just the data itself. So I recommend using PGI if you want to try out the managed memory. But CRAID may have an option for that as well. If anybody knows if CRAID does, please comment in the OpenACC channel. Any other questions? All right. I'm going to talk briefly about asynchronicity between the CPU and the GPU. So why would you want to do things asynchronously? The number one reason is to overlap independent tasks. So if you have some chunk of work that would not thread very well on a GPU, and it can be done in completely parallel with GPU work, you can use the asynchronous clause in OpenACC, which is just like async. This is just like streams in CUDA, essentially, and the way they implement it under the hood is streams. The same is true for OpenMP offload. They claim that there's data dependency, but if you actually look at what's going on, they're using streams under the hood. So you might as well just create an imaginary integer and depend in and out on that integer, but that's OpenMP. So we'll get back to OpenACC. There are lots of cases, for instance, where you want to have transfers between the CPU and the GPU operate asynchronously with the GPU launch or with CPU code. So you can use async on data statements. You can use async on kernels. And you can use those to allow overlap with one workload with another with data copies, for instance. So you could presumably have data going to the GPU and to the CPU and CPU work and GPU work happening all at the same time using async clauses in OpenACC. Another reason you might want to use asynchronicity is to have these streams handle complex workflows that have dependencies. And so maybe you have one pipeline of workflow that has a set of dependencies, and you have other parallel pipelines with other dependencies, and you want to just make sure that those dependencies are met and just launch it all. Asynchronous streams in OpenACC is one way that you could do that. Another thing that you can do is if you have a bunch of small kernels, say, that are running on the order of 1 to 5 microseconds, the problem with that is that the kernel launch overhead on the GPU is typically about 10 microseconds for current GPUs. So if you have a lot of small kernels that are happening in succession, you can launch them all asynchronously, and you will actually be overlapping the kernel launch overhead with kernel execution. And so you can reduce the overall overheads of all the launches when you have a lot of small kernels. This is something we use liberally in Climate because we have a ton of kernels that run extremely quickly because we don't have the parallelism available in our model because we have to run super fast and strong scale, so there's not much parallelism to be exposed. So in our case, we launch everything asynchronously for the sole purpose of hiding the launch overheads. This is the syntax that you would use. You would have some sort of clause, either data or kernel, and you put it async with some sort of integer value. It can actually be an integer. It doesn't actually have to be an integer literal. So you're free to do that. And you don't have to actually put an integer. If you don't put anything in there, it'll be in the default async ID, which is pretty similar to the default CUDA stream. Although there's not a one-to-one matching there. You're not guaranteed that just putting async with no number will launch in the default CUDA stream. I don't think that actually happens. The OpenACC runtime will create a CUDA stream for you that's the default, and that's what it will run under. So if you want to synchronize your CPU work with something that was launched asynchronously, you use this wait syntax, where if you launched with async with no number, you would just say $ACC wait or pragma ACC wait. But if you actually specified an integer stream, you would have to put that integer stream. If you say ACC wait without any integer parameter there, it will wait on all of the asynchronous IDs for the kernels before it continues in the CPU work. So this is similar to an OMP barrier in nature. So that's all I have for the presentation. The hands-on exercise is available on GitHub. I think I saw a comment that someone said they had permissions issues. So can y'all check this out real quick in here and see if you're able to access this markdown file? Does anybody have problems accessing this? It should also be in the OpenACC Slack channel. You shouldn't have to type this address yourself. Has anybody gotten there yet? Oh, okay.
I've opened every link that you posted just fine.
It opens fine? Yep. Okay, for whoever posted the permissions issue, I'll try to see if I can figure out what that permission is. If you could give me as many details as possible in the Slack channel, I'll try to check that out. But this is the hands-on exercise for this. A little bit of information about the hands-on exercise. It's a code called MiniWeather. And these instructions should be pretty self-contained. They point to the documentation of the model. What this does is it simulates a simple weather-like flow using what are called the Euler equations, which is Navier-Stokes without diffusion, at least without this explicit diffusion. And so you can simulate flows that look like weather fronts, that you can see a lot of the turbulent eddies that happen when you inject a high-velocity flow. So it's meant to train in NPI, OpenMP, and OpenACC. So these instructions here should be pretty self-contained about how to get this code working with OpenACC. I've given a lot of directions you could take with this. You can add your own OpenACC directives, or you could just look at the already existing OpenACC file to just kind of learn. You could take this and practice your debugging chops on the GPU by running things like CUDA memcheck and valgrind on the code, and all of those instructions should be there. If you have any questions about this, just post it to the Slack channel, and as soon as I can get to it, I'll try my best to figure out what's going wrong.
There was an interesting question. What is the best way to handle multiple GPUs using OpenACC?
Great question. What's the best way to handle multiple GPUs? I would not handle multiple GPUs in OpenACC. I would run one MPI task per GPU. This is made really easy on like OLCF Summit architecture, where you can use what are called resource sets in your JS run command, and you can just have one resource set per GPU. And so when you actually launch your job, all the process within a resource set sees is the GPU allocated to it. There is a way, if you go to the openacc-standard.org and look at the specification, there is a way to specify the GPU that you want to run on. But it does get very complicated. So I strongly recommend just one MPI task per GPU and let that be that. I'll see if I can scrounge up an example of how to do multiple GPUs. What you're going to essentially have to do is you're going to have to manually fission the work yourself, say on the outermost loop, and just allocate different chunks to different GPUs manually. Where there is a clause in OpenACC where you can specify what device something is launched on. But by far the simplest, and what almost everybody does, is to just run one MPI task per GPU on a given node. Are there any other questions?
There was one other one a while ago, but this seems like a good time.
Yeah.
With advances in OpenMP, what is the future for OpenACC?
Okay, the question was, with advances in OpenMP, what is the future of OpenACC? That is not a question I am qualified to answer, and if you ask different organizations and people, you will get very different answers. So it's a very political question to ask, and the answers are going to be very political. When I first saw OpenACC, the way I viewed it was a stopgap for GPUs until OpenMP could actually include the functionality we need for GPUs. But OpenACC has seemed to kind of create its own niche and its own world. So will OpenACC go away in the future? I can't answer that. All I can say is our project is very keenly looking at changing to OpenMP offload. But yeah, I really don't think I should answer that question much more than that. They're both effective at what they do. OpenMP's GPU offload is fast developing, but if I had to say, as far as performant options, I think OpenACC is still currently faster with the PCI and Cray compilers at the moment, but that's going to change over time. Any other questions?
So which library do you think has the best practice
That's the best.
for using OpenACC to port the...
Which library?
Yeah, do you have an example?
To
Which
learn
library
OpenACC?
people using the OpenACC to port their code? Very good example that we can look into.
The question was, are there any good libraries we can look into to see how somebody ported their code
Yes.
to GPUs using OpenACC? That's a hard question to answer because libraries typically don't use things like OpenACC because they want to optimize as much as possible. So some libraries are coding at the PTX level on the GPU, and most libraries are coding at the CUDA level. So very few are going to use OpenACC. We ported our climate code to GPUs using OpenACC, and in the other resources at the Markdown file that's shown on this link currently, I do put a pretty detailed guide of what we had to go through to port a CPU code to OpenACC from scratch, and what do you typically have to go through to do that. So maybe that'll be helpful as an example of what typically happens. I should have mentioned this up front, honestly. Typically, learning the OpenMP syntax and semantics is like maybe 3% of the actual porting effort you're going to do. The vast majority of your effort is going to be refactoring your code to expose this threading in the first place. And that is a very difficult task and usually very involved for most codes. So OpenACC is typically just syntactic sugar to get stuff on the GPU. But the real work is exposing the threading yourself. And so that document at the bottom of this Markdown file, it gives an example of what it looks like for a realistic code to have to go through this. So maybe that'll be helpful. Hopefully that'll be helpful to you.
Okay, thank you.
Yes.
You mentioned in the beginning there are better options for C, C++. What are those options?
Okay, so I'm about to make another political statement. If you are in C or C++, I strongly believe you should be using your own multidimensional array type that has a shallow copy that you can use pass-by-value lambdas to send to some sort of kernel launcher. And what that essentially is either Cocos or Raja. But it's actually not that hard to code yourself. The reason, so Cocos and Raja, they're a C++ portable version of CUDA. That's essentially what it is. You were specifying what a kernel does over a single thread, and you're saying, here's how many threads to launch. And then you're passing the kernel itself typically as a lambda, because that's much easier to write than an explicit functor in C++. So if you're in C or C++, this is probably the most portable and performant option you can do. I don't think OpenACC is the best option there. Where I think OpenACC really shines is Fortran code bases. So again, that is a political statement, but I definitely stand by it. I've tried a lot of different options, and if I'm in C++, I usually find it much easier to just create a kernel launcher and to send lambdas with shallow copy arrays as data types. Because then you can take that kernel and you can either put a for loop around it with a little vectorization pragma, or you could put CUDA syntax around it, or you could put OpenCL if you want to run on, you could put Sickle, you can put anything you want on it, because you have the work exposed as a C++ lambda or as a functor. So if you're in C or C++, if you want to be portable, I strongly recommend you use one of those options. They are currently more portable than OpenACC. That may not be true in the future, but that's the current state of the art.
Can you call a CUDA library within OpenACC?
Yes, you can call CUDA within OpenACC. I don't have any examples in the slides, but there's this ACC calls, I believe it's device pointer or something like that. But what it will do, if say you're in Fortran, for instance, you have a data, again, OpenACC thrives on mirroring data between the CPU and the GPU. So if you have something that's mirrored between the CPU and the GPU, you can put this ACC clause that everything inside that clause, if you access that array, it's the GPU pointer. And so you pass the array like normal to the library, but if the library is expecting a GPU pointer, inside those OpenACC statements, it will be a GPU pointer. So that's for C and Fortran. That's the most common way you interoperate between CUDA and OpenACC. There's also OpenACC runtime library routines that will expose the CUDA stream from an OpenACC async ID. Yeah.
Okay, I don't see any other questions in the Slack channel. If you have them, please go to the OpenACC channel and ask them. Matt will take a look through that and see if there's anything that has not been addressed to answer. So we'll thank Matt for his presentation. Are you just into the hands-on at this point?
Yeah, this is hands-on time from here out. So if you have any issues or questions, post them in one of the Slack channels, and I'll get back to you for a second.
Okay, very well. So we'll, I guess, turn things over to the team at NCSA for where you want to go from here. But we are in the hands-on for the rest of the day.
We'll keep the channels open until people depart. And we'll see you bright and early tomorrow. Thanks to the Oak Ridge team.